This is the second part of Experiment 4 from Charles Platt's Make Electronics, second edition. We're going to take a look in some more detail at the dimmer switch circuit that we built and talk about the steps you have to take to successfully construct circuits in a bit more detail, including their measurement. The first thing is, of course, to measure components. So far we've only talked about determining the value of resistors by checking the resistor code and measuring with power off from a resistor. Following the circuit diagram with a pencil at the same time as you look at the actual components is for the moment your best route to success in getting a circuit properly built. Once built, then the obvious thing to do is to check if it performs as expected. In the case of the dimmer switch, we expect to see that as we decrease resistance, the light gets brighter, and as we increase resistance, the light gets dimmer due to less current in the circuit. Now the fourth step, one we're going to focus on today, is measuring the voltage across each component. So in this case, I'm measuring the voltage across the variable resistor, two of the leads, say the center and right lead of the potentiometer. And I find that the voltage increases as I increase resistance, meaning that with more voltage drop across the resistor, there is less to light up the light. Notice how the current increases as the resistance goes down, and at the same time the voltage across the resistor also changes. Now we're going to try something new, which is a current measurement. This is very important that you do it properly because it is possible to blow the fuse inside your meter if you don't do things quite right. The process for measuring current, which is like sticking a paddle wheel into a flowing river to measure the current flow, is that you interrupt the circuit and insert the current meter in through the circuit. Again, this is very different than voltage, which we measure across a circuit. Current we measure going through a circuit. When you construct your circuit, it's going to be off initially because you've broken it to insert the current meter, and only when you touch the leads from your meter, allowing the current to flow through the circuit, is it going to turn on. Notice we're in the amps mode, and that on some meters you have to switch your probes from the volt to the milliamp setting in order for this to work. Again, only when I physically touch and get myself on the proper scale do I see the circuit function, and then I can watch the current on my meter. It's measuring in milliamps right now, and of course the current increases as the LED gets brighter, depending on where I put the potentiometer. The proper way to view this process is even using the current meter is you're letting all the current flow through the meter so that it can be measured. That's why some meters, again, require that port to be moved. Now let's look at the behavior in a little bit more detail. Here we are in a dim setting. If I crank it all the way up to the smallest resistance, which for the center and right leads of the pot is all the way clockwise, I get my highest amperage reading, 15.45 milliamps. And I know from past measurements that's going to correspond to the brightest LED, the largest voltage drop across the pot, and of course, as now I can measure directly, the most current across the circuit. 7.6 milliamps is somewhere in the middle. The final step in circuit analysis is to put your circuit back together so it's functioning without the meter in there, and switch back to voltage mode. And now we're going to systematically probe around the circuit at each point to try to understand exactly what's going on in the components. And the rule that we're going to talk about is that all the component voltages need to add up when taken individually to the voltage of the battery. So here I am looking again at the resistor, and I kept a second current meter in the circuit just in the simulation so you can see what's going on. Now I go over and I interrogate, I probe what's happening in my light source. Now of course if you're using an LED in the actual experiment, you will find this voltage is pretty much always the same for a red LED, about 1.93 volts. In the case of a real light bulb, it'll change slightly. And then I go over and I check the power source because I really only have 3 components. And notice how now I'm keeping the common probe on the negative terminal of the battery and moving the probe around to probe each location in the circuit sequentially. Let's use some numbers and a real case here to check this out. So first of all, with my meter back in the volt setting, I'm going to check out the battery voltage. Should be close to 9 volts, of course. Now I'm going to go up and measure the voltage across the resistor. At this particular resistor, I'm getting 7.50 volts. Now I'm going to measure across the LED. As a quick caution, if you're measuring no voltage across your LEDs, that means you've got to reverse your probes. You have to measure the voltage counter to the current flow direction LED. So you should see about 1.93 volts. Now if I add 7.5 to 1.93, I get 9.43 volts, and that of course is essentially my battery voltage. This is the check you should do in any loop circuit to make sure that you understand what's going on. Again, the sum of the voltage differences for each component around a circuit loop needs to equal the actual voltage that you're putting in from a power supply, in this case a battery. Now this rule is mentioned in the textbook. It actually has a fancy name. It's called Kirchhoff's voltage law, and it's actually a specific case of a more general rule in physics called the conservation of energy. That is, the energy you get out of the circuit by going through it, you have to put in by putting into a battery. Now there's one other general rule that we should talk about right now, which is called Kirchhoff's current law. And it says, in simplified form, that the current has to be the same anywhere in a current loop. So if I put my meter, for instance, in the figure on the left before the LED, or in the figure in the right after the LED, I should measure the same current each time. And that's always going to hold unless there's a fork in the road. If the circuit has a junction, then we need a more complex version of this law. It's a manifestation of a broader physics principle called the conservation of charge, which says that any charge that enters the circuit from the, say, positive terminal of the battery has eventually got to go back to the negative. And if there's no branches in the circuit, there's really nowhere for it to go except to return via the one loop you have in your circuit. You should definitely put this law to test and try moving your current meter around to different points in the circuit of a simple loop like the ones we've been building, making sure you always get the same answer. It is very important that you try to repeat some of these measurements and develop a facility. Remember, the voltmeter is your eyes and ears when dealing with DC electrical circuits. There's no other really way to know really what's going on except maybe watching if the circuit works as it behaves. And if it doesn't work, you need ways to troubleshoot. So again, building an intuition for using the meter in both current and voltage and resistance mode to understand and troubleshoot your circuits is a really important skill to be developing at this point in the class. For that reason, I'm asking you to follow the directions given in the textbook for the making measurements sub-experiment, which is described on pages 27 and 28 of the second edition and in figure 1.57. Asks you to turn the potentiometer fully clockwise, fully counterclockwise, and then somewhere in the middle, and compare the current and voltage readings you get in each of those 3 settings. And then it goes on to describe a calculation you can do using a rule called Ohm's law to figure out if your numbers are approximately correct or not. Please go through this exercise. We'll be dealing a lot more with Ohm's law in experiment 5 and developing the relationship between these 3 constants, current, voltage, and resistance, with more quantitative detail. So it's important to get some hands-on lab experience first.